All right, so let's start the problem solving for chapter 6. All right, so let's start with question number 1. And here it asks us to calculate the work done. Okay. Now it gives us the force. Okay, so it gives us the force. It gives us the displacement. It gives us the angle between the force and displacement, and solving the work done for this problem is very simple because all the information we need are given. Okay, so straightforward, just plugging the number in this equation. Okay, so F is 75 Newton, displacement is 25 meter, and cosine 35 degree. Okay, so if you plug all these three numbers in your calculator, you should get something like 1536 joule. Okay, all right, the next problem is also simple. Okay, again the force is given, the angle is given, and the displacement is also given. So again it is very simple. Okay, just plugging the numbers. So W equal to F D cosine theta. So F is 50 Newton, D is 30 meter, and cosine 30 degree. So plugging these values in calculator gives me 1299 joule. Okay. All right, so these two are not that bad, just plugging the numbers. So now let's move on and see that whether we have some complicated problem. All right, the next problem is this one. And it looks like, okay, so the so it's so here it gives us some velocity. So velocity equal to 22 kilometer per second. Okay, some object's velocity is given, and also the kinetic energy is given. Okay, so this is the kinetic energy. Okay, so it says that some asteroid some asteroid hits somewhere, I mean this place. Okay, and while it is hitting the ground at this, it releases this much of kinetic energy. So we have to calculate its mass. Okay, now what we need to know here is the definition of the kinetic energy, right? So the definition of kinetic energy is half mv squared. Okay, so we know the kinetic energy, we know the v, so we can determine mass by solving this. Okay, so how to solve this? We can determine mass. I mean, let's solve this equation for mass. So it will be 2 times the kinetic energy divided by the velocity square. Now here you see the velocity is not given in the correct unit. Okay, so velocity is given in kilometer per second. So what we have to do, we have to convert kilometer to meter. Okay, and we already know that how to convert. Okay, so now it just becomes meter per second. Okay, so in this equation then what we have to do, 2 times kinetic energy is 4.2 times 10 to the power 23 joule, and then v square is 22 times 10 to the power 3 meter per second, and then the whole square. So then what we have to do is just plug this number in calculator, and plugging this calculator gives me this number. So check that whether you get this number or not. Okay, and the mass should be in kilogram. Okay, so kilogram is the correct unit for the mass. I mean the standard international unit for mass. So see that whether you get this or not. Let's move on. The next question. Okay, so here it asks us to calculate the force needed to bring 950 kg car to rest from a speed of 90 km/h in a distance of 120 meter. Okay, so what we are given here, we are given distance d equal to 120 meter. Okay, we are given the mass of the car is 950 kilogram. We are given the initial speed v1 equal to 90 km/h and v2 is equal to 0. We have to calculate the force. Okay, now everything are in a good shape except the v1. Okay, v1 is given in km/h, so it's not useful. Okay, so let's first convert it into useful unit. Okay, so 90 times 10 to the power 3 and then 60 for second, 64 minutes, 64 second, that is in meter per second. So if you plug these values in your calculator, v1 will be 25 meter per second. Okay, so v1 is 25 meter per second. Now now all are in good shape. Okay, now we have to think which equation is useful to solve this problem. So we are given the distance or the stopping distance. So you can say that this is the stopping distance. We are given the mass of the car. We are given the velocity, initial and final velocity. We have to calculate the force. Okay, you probably already thinking about the work kinetic energy principle, right? So work kinetic energy principle tell us that W net is equal to change in kinetic energy, and then change in kinetic energy is kinetic energy final minus kinetic energy initial, and W net is F times D, right? So we have to calculate F, sorry, D, no, F, right, F. So F equal to then kinetic energy 2 minus kinetic energy 1 divided by D. Okay, and the kinetic energy 1 equal 2 is equal to 0, right? Because the velocity, final velocity is equal to 0, so the corresponding kinetic energy will also be equal to 0. So our equation is now very simple, minus kinetic energy 1 over D, and you know that kinetic energy of a particle is mv1 square, right? So it is 2d mv1 square. So now plug this value, the given values here, it will give you the number. Okay, so if you plug these values in your calculator correctly, you should get, so I got something like this, minus 2474 Newton. Okay, so for the first problem, number A is minus 2474 Newton. Okay, now Now, the second one, it tells that suppose instead the car hits a concrete wall, concrete abutment or wall at full speed and is brought to a stop in 2 meters. Okay, so if instead of 120 meter, if the displacement is 2 meter instead of 120 meter, what is that force? Okay, so here when the car stops in 120 meter, we see that the force is 24 or about 2500 Newton. Okay, now instead of 120 meter, if it is just 2 meter, what will be the force? Okay, so you can do the same thing here. You just replace 120 meter by 2 meter and then calculate the force, the new force. Okay, so when you replace this 120 meter by 2 meter, you will get a huge number. Okay, I got minus 148,438 Newton. Okay, so you see that it's huge number. Okay, so when the stopping distance is small, the impact force is large. Okay, so you see that impact force is large. Okay, all right. All right, the next problem. In the next problem, we are going to use the conservation of mechanical energy. Basically, next few problem, it looks like we are going to, no, first we are going to use the potential energy. It looks like the next problem is the potential energy problem. All right. Yeah, so here in this problem, we are going to see that changing the reference point will change the potential energy, but then the change in potential energy is still constant. Okay, still the same. Okay, so when you change the reference point, okay, you will see that the potential energy changes, but the change in potential energy, that means the delta PE is the same. Okay, no matter what reference point you are using, delta PE don't change. Okay, all right. So here it asks us to calculate the potential energy at several points. So for example, here we have this track and the roller coaster car. So mass of the roller coaster car is given 1000 kilogram and it is moving from point 1 to point 2 to point 3. Okay, and it asks to calculate the potential energy at position 2 and position 3. Okay, so for the first problem, number A, it says that calculate the potential energy or absolute potential energy at position 2 and 3, and for this use this as the reference point. Okay, use this line as your reference line. Okay, so let's try to calculate number A. So potential energy at position 2 will be mgy2, right? So m is 1000 kilogram and then g is 9.80 meter per second square, and y2 is, we have to determine the distance from this point, right? So if it is 0, so from here to here is 10 meter plus 10 meter. Okay, so this is 10 meter. So what we get is 9.80 times 10 to the power 4 joule. Okay, how about potential energy 3, mgy3, and then again 1000 kilogram, 9.80 meter per second square. But what is the y3? So y3 is, so from this line to this distance. Okay, and you see that this is the y equal to 0 line, and below this 0 line all number is negative. So what we get is 15 meter, but it is negative 15 meter. Okay, so remember that if you don't plug the negative value, your potential energy will be incorrect. Okay, so the potential energy at this point is negative, and then if you plug these values in your calculator, it should give you something like this, minus 2.45. No, sorry, I got minus 1.47 times 10 to the power 5 joule. Okay, so you see that the potential energy at position 2 is this, at position 3 is this, when our reference line is this one, okay, from which we measure the distance. So above this line all the number is positive, below this line all the number is negative. Okay, all right. Now number B. So what is the change in potential energy? Okay, so the change in potential energy is delta PE, and delta P is final potential energy to initial potential energy. So final here is 3 and initial is PE2, right? So minus 1.47 times 10 to the power 5 joule, and then minus 9.80 times 10 to the power 4 joule. And this will give me minus 2.45 times 10 to the power 5 joule. Okay. All right. Now number C. Okay. It says repeat parts A and B, but this time takes the reference point y equal to 0 to be at the point 3. Okay. So now it says that take this line as the reference point. Take this line. Okay. All right. So PE2 is again mgy2. M is 1000 kilogram. The gravitational acceleration is 9.80 meter per second square. Now from here to position 2 is basically 15 plus 10, 25 meter, and it will be positive because it is above the y equal to 0 line. So what I get is 2.45 times 10 to the power 5 joule. PE3 mgy3, 1000 kilogram, 9.80 meter per second square, and then it is 0 meter because from here to here it is 0, so it is 0 joule. Okay, so you see that PE2 and PE3 change, right? When you change the reference line, they change. But now let's see that whether delta PE changes or not. So delta PE will be again PE3 minus PE2, right? Final potential energy minus initial potential energy. So final is 0, minus initial is 2.45 times 10 to the power 5 joule. So you see that it is exactly equal to what we got earlier in number B. So you see it is minus 2.45 times 10 to the power 5 joule. Okay. All right. All right, now let's move on. Number 6. All right, so we have a perfectly elastic spring that requires 0.54 joule of work to stretch 6 centimeter from its equilibrium position. Okay, what is the spring constant? Okay, now you probably remember that the work done we calculated for the spring force or the external force in that section is something like this, half k x square. Okay, now here the work done is given, the x displacement is given, so we know w, we know x, we can solve it for k, the spring constant, right? So let me write down w equal to 0.54 joule, and then x equal to 6 centimeter. Okay, 6 times 10 to the power minus 2 meter. Okay, you know that centimeter is not a useful unit. For us, the meter is the useful unit. So these are given. We have to calculate the spring stiffness constant k. So what we have to do, we have to solve this equation for k. So what we get, k equal to 2w, 2 times w divided by x square. So 2 and then 0.54 joule, and x is 6 times 10 to the power minus 2 meter, and then whole square. So this gives me 300 Newton per meter. So the spring constant for this problem is 300 Newton per meter. Number B, okay, how much work is required to stretch it to an additional 6 centimeter? Okay, so now the displacement is 6 centimeter plus 6 centimeter, right? Additional 6. So in the first problem, it says that the 6, it already stretched to 6 centimeter. So additional means we have to add them. So we get total 12 centimeter. Okay. So 12 centimeter means 12 times 10 to the power minus 2 meter. So if so, what is the work done? So work done will be half k x square. So half k is 300 Newton per meter, and then x square is 12 times 10 to the power minus 2 meter, and then that is square. So the work done for this case will be 2.16 joule. Okay, so this tells us that the additional work done we need, okay, let me call it additional, that will be equal to 2.16 joule and minus 0.54 joule, because this 54 joule we already have, right? I mean, this 0.54 joule is already needed to stretch the spring by 6 centimeter. The question asks that what more work done we need to stretch it 6 more centimeter. So the additional work done we need is 2.16 minus 0.54 joule, and that is equal to 1.62 joule. Okay, so you have to be careful here. It didn't ask you to the total work done. It asks us to the additional work done we need here. Okay. All right. So here you see that by stretching it 6 additional centimeter, it doesn't require just the 0.54 joule of energy. It takes like 1.62 joule of energy, which is about 3 times. Okay, so for the first first 6 centimeter, it takes 0.54 joule of energy. For the next 6 centimeter, it takes like 3 times of 0.54. Okay. All right. Number C is tell us that how much work is required to compress the spring 6 centimeter from its equilibrium position. Okay, and it's easy to calculate, because we already know that when x equal to 6 centimeter, the work done we required is 0.54 joule, right? Now it doesn't matter whether you are stretching or it is or you are compressing. Okay, in both cases we need the the same amount of work done if the displacement is same. So because we already know for this 6 centimeter, stretching the spring by 6 centimeter, it requires 0.54 joule. So compressing the spring by the same amount, okay, it will need the same amount of work done. So without calculating, you can say that the work done we need is 0.54 joule. All right, the next one is using the force versus displacement graph to determine the work done. Okay, all right. So you know that when we have a force displacement graph, then the work done is basically the area under the graph. Okay, so now here it asks us to calculate the work done when the displacement is displacement is 10 meter between x equal to 0 and 10. So the first one is this. So the area under the curve will be just this area. For the second one, we have to calculate the both this and also this. Okay. So first let's calculate the first one when the displacement is from 0 meter to 10 meter. Okay, all right. Now you see that this is not a triangle, right? In the theory class we see that the shape was triangular, so it was easy. It looks like a trapezoid shape. So it looks like a trapezoid shape. Okay. So what is the area of a trapezoid? So the area of a trapezoid, if you remember, if you don't remember, just Google it. But here it is. So the area of a trapezoid is half the top base. So base, let me call it base top, and then base bottom. Okay, so base means, so this is the base, this is the bottom base, and this is the top base, and this times height. So this is the height. Okay, so the top base, the bottom base times the height. So top base, so now we have to find what is the top base. Okay, so the bottom base, it looks like 10. So let's plug the value for the bottom base. It is 10 meter. The top base looks like okay, so it looks like 1 2 3 4. So from here, okay, so this is 1 2 3 4. So it looks like the top base is 4 meter, and then height is this height, so it looks like 400 Newton. Okay, so if you calculate this, you should get 2800 joule. Okay, so the work done, okay, for the first one is 2800 joule. So this is the number A. Number B, it says that what is the work done when it goes from 0 to 15 meter. So for this one, for the second problem, we have to add this one with this one. Okay, so because we have already this one, okay, let's first calculate the small one and then add them together. Okay, so the small the trapezoid would be half, again this times height. Okay, so half, top is easy to understand, top base is 5 here, right? So this is 5, so 5 meter, plus bottom is so it looks like this one, and then this one, so it looks like 2, so from here to here is 2 meter, and then height is this one, right? Negative 200 Newton. So negative sign is very important here. If you don't write the negative sign, you get an incorrect answer. So this area, the small trapezoid's area, is basically 700 joule. Okay, so when you add 2800 and negative 700 joule, it gives me 2100 joule. So the area, the work done when it goes from 0 to 15 is 2100 joule. Okay, so the negative sign, many students make mistake here, they forget the negative sign, and then they get 3500 joule. So that is incorrect. Make sure you understand there should be a negative sign, and then you have to subtract this. Okay, so 2800 minus 700 is 2100 joule. All right. All right, so let's try this one and the next one, and then the rest of the things we will be doing in the next class. Okay. All right, so here it looks like the original height of the rock in the figure is 3 meter. So at this point, this is the height of the original height of the this rock. We have to calculate the rock's speed when it's fallen to somewhere here. So when the height from the ground is 1 meter. Okay. All right, so how to solve this problem? So at this point, what energy we have? So we have to understand that what energy this stone has at this point, at this position. So because the person is holding this rock, okay, so it will not have the kinetic energy. So at this point, let me call it position 1, and at this position the kinetic energy is equal to 0. Okay, the potential energy will be mg 3 meter. Okay, so whatever is its mass times the gravitational acceleration times the height. Now at this point, when it is 1 meter from the ground, so that is our position 2, at this point we know that the potential energy is mg 1 meter. Okay, and there will also be kinetic energy. Kinetic energy will be 0 here. I mean, after it hits the ground, then the kinetic energy and all the energy basically converted into something else, the thermal energy or sound energy or the light energy. Okay, but we will have kinetic energy here. Okay, and that will be half m v2 square. Okay, and basically we have to ask to calculate the v2 at this position. Okay, so you see that the mechanical energy we have here is this one, I mean the sum of these two, and the mechanical energy at position 2 we have this. Okay, and let's neglect the non-conservative force. I mean, neglect the air resistance and the friction. Okay, so if we neglect the air resistance and the friction, then we can use the conservation of mechanical energy, right? The conservation of mechanical energy tells us that kinetic energy 2 plus potential energy 2 equal to kinetic energy 1 plus potential energy 1. Okay, and we already know that this is 0, so it's very simple now. Kinetic energy 2 equal to potential energy minus potential energy 2. Okay, so it is half m v2 square, and PE1 is mgy1, and it is mgy2. Okay, so you see that m is common in all the terms, so I can cancel m. So what we have here is half v2 square equal to, okay, now then v2 square equal to 2 times, okay, or v2 is basically square root of this. Okay, now we can plug the values here. So 2 9.8 meter per second square, and then y1 is 3 meter and y2 is 1 meter. Okay, so plugging all this in your calculator correctly should give you this value, 6.26 meter per second. Okay, all right. All right, so this is the last problem for this lecture, and then in the next class we are going to do more. All right, so we have a track, roller coaster track and roller coaster track car, and it says that this height, the initial height is 40 meters. So this height is 40 meter, and at this position the car is at rest. Okay, the car starts from rest at the top of the hill. Okay, calculate the speed of the roller coaster at the bottom of the hill. So we have to calculate the speed at this point. Okay, it is the first one, and the second one, it tells us that at what height it will have half of this speed. Okay, so first let's calculate the first one and then move to the second one. Okay, so here let me call this position as the initial position, this position as the final position. Okay, so at the initial position the kinetic energy is equal to 0, right? Because the car is at rest. All the energy is potential energy, and potential energy will be mgy1. And now number 2, there will be kinetic energy, that will be half mv2 square, but the potential energy at this point at position 2 will be 0, because the height at this point is equal to 0, because we are measuring the height from this position. Okay, so again, if we neglect the friction, because it didn't mention, the question didn't mention about the friction, so we can neglect it. So if we neglect the friction, okay, then we can use the conservation of mechanical energy, and then conservation of mechanical energy tells us that ke2 plus pe2 equal to ke1 plus pe1. So P2 is equal to 0, K1 equal to 0. So the equation is very simple now. Half mv2 square equal to mgy1, and m cancel out. So v2 square is 2gy1. So v2 is basically square root of this, and this is equal to is equal to 28 meter per second. So I got the speed of the roller coaster at this point is 28 meter per second. Okay. Now the next question. So this is A. Now the next question, it asks us to find the height, this height, when the car speed is 14 meter per second. Okay, so it says that what is the height? It will have half this speed. I mean, at what height the speed will be half of the speed at the bottom. Okay, so we have to find that. Now let me call it position 3. Okay, all right. Now so at position 3, PE3 equal to mgy3, and the kinetic energy 3 is half mv3 square. Okay, now let me use this equation. PE3, this is our final position. The initial position is PE1 plus KE1. Okay, so you can also use the, on the right hand side, you can use the potential energy 2 and kinetic energy 2. It doesn't matter. Okay, so let me use PE1 and KE1. So here we have mgy3 plus half mv3 square, and here we have mgy1, but that is equal to 0. Okay, so again m cancel out. So y3, actually gy3 is gy1 minus half v3 square. So y3 will be y1 minus half. Okay, so something like this. Now if you plug this value and plug the given values here in this equation, you should get, so this is 40 meter and then minus 9.80 meter per second square, and then v3 is 14 meter per second whole square. So if you plug all these values in your calculator correctly, you should get the height is equal to 30 meter. So at y equal to 30 meter, the speed will be half of the speed at the bottom. Okay, so the speed will be 14 meter. All right, so I'm going to stop it here for this lecture. We have few more problems to solve, so we'll be doing it in the next class.